me start the recording. It's a great pleasure to have Filip Dul talk to us about general covariance from the viewpoint of stacks. And I've reminded him that we have no clue what this is, so he's going to be very elementary, right, Filip?
Yeah, absolutely. So thanks, thanks, Shadi, for the introduction, and it's nice to meet you all. I'm excited to join your group in a few months. So today I'm going to be, the title is kind of long, right? General covariance from the viewpoint of stacks. This is going to be somewhat of a summary of my thesis work, but I think the goal for today for me is going to be essentially to use physics language combined with some like categorical language, but at an introductory level, to sort of convince others of the usefulness, right, of things like groupoids and stacks and this kind of thing. When I was learning about these perspectives, coming from a very analytic, very physical background a few years ago, I was a little bit intimidated, but over time, given the right teachers, which I did have, I was able to make sense of it. And hopefully this will serve as a reasonable introduction for many of you. And so first, I'm just going to make a few remarks and go over a quick example. And then I'll tell you about groupoids and stacks. It's sort of using the example of general covariance as a way of keeping things concrete. And then at the very end, I'll talk about how some perturbative computations can be nicely summarized using stacks, but on a more like formal or local level. We'll see what that means in a bit. Let me see what time I'm starting. Okay, 12:12. So as some of us might know, general covariance has a pretty long history. The basic idea is that if we have a manifold or a spacetime for many of us, then the diffeomorphism group might be a symmetry of something associated to a field theory, right? So if you have a boson or a fermion or something like this, living in your spacetime, you have an action functional, and the diffeomorphism group might be a symmetry of some related physics. And so we're going to follow the path that was laid out in the 20th century with general relativity. The idea here, of course, being that we have field theories that are coupled to Riemannian or Lorentzian metrics, which from here on out, I'll just say semi-Riemannian because my constructions work for both. So just as a quick reminder, if you have a manifold or a spacetime, its diffeomorphism group, which I'm usually going to denote as curly D, because the manifold will usually be implicit. This is the group of all smooth functions from the spacetime X to itself. And there are a few interpretations that one can take about this group. There's passive transformations, active transformations. This is kind of discussed a lot, actually, more so in physics literature than math literature, as far as I can tell. But usually we can view it simply as a group of coordinate transformations for a manifold X. So I'm going to do a quick example to begin with, and this is sort of the example we're going to be referring to throughout the talk. By the way, before I move on, I would like to say that if anyone has questions, please let me know. I prefer it when my talks and seminars are more interactive, and I think I have sort of a bad habit of moving quickly. So if people can help me break that habit, that would be fantastic. Okay.
I have just a brief comment, even though here in this audience, there's, I think everybody knows, of course, you said smooth functions from a manifold to themselves also have to be invertible. No? So it's.
Yes, that's right. Thank you very much. I did not state that. But yeah, like Professor Kiesling said, they have to be smooth and invertible. So diffeomorphism, I mean, it's like the smooth version of a homeomorphism. Right, where you have a map from a manifold to itself, and all of the coordinate functions are differentiable, or at least differentiable and invertible.
I just pointed out it was not on the slides. I know that you know it, and we know that also.
Yeah, but that's great. No, it's good that you mentioned that. It's of course good to be careful always. Okay, so here we're going to consider the example of the massless scalar field. For us, this means that we just have this smooth function phi on the spacetime X, and we fix a metric. This notation on the right-hand side here means we have the space of all metrics on the spacetime X, which I'll just denote as curly M, again, because X is implicit. And the action functional we're going to be considering is some sort of, it's a classic that many of us probably know, right? The integral over the manifold of phi Laplace phi times the Riemannian volume form. Of course, the idea is if you compute the Euler-Lagrange equations associated to this action functional, then the the critical locus of function x harmonic with respect to this particular Laplacian. And this equation of motion here, or rather the Euler-Lagrange term on the left-hand side, has a very interesting quality. If you fix a diffeomorphism f, then it sort of commutes with the Laplacian in this sense, where the pullback of a Laplacian of a smooth function of a scalar field is the Laplacian with respect to the pulled back metric of the pulled back scalar field, right? So I would say that this is saying that the action of the diffeomorphism group commutes with the Laplacian. A lot of people would say, of course, the Laplacian here is equivariant with respect to the action of the diffeomorphism group, or with respect to coordinate changes. Again, there's a few interpretations; they're all equivalent, but whatever floats your boat. And so there's a key maneuver, and this is where things get a little homological. Is, well, I'll go back for just a second. Note that in this case, we just had the scalar field phi. It was a smooth function on x. We called this the scalar field. Now, instead of just having a vector space be the space of fields, in other words, C infinity of x is a vector space, we define a differential graded space of fields. This is a differential graded vector space. So in degree 0, we put the usual sort of naive scalar fields. And in degree 1, we put a sort of dual of what's in degree 0. This notation, this brackets -1, for those that haven't seen this before, that means that we're placing the space of densities on x in degree 1. I know the notation's not that great, but it's just what's in the literature, so I have to use it. And the differential between what's in degree 0 and degree 1 is really just the linear map, right? Is we take a smooth function phi, and we hit it with the Laplacian, and we include also the volume form so that it lands in densities. And it's also practical to have the volume form because it actually, now the differential includes all of the dependence on the metric from the original action functional. So that's another benefit. So just a sort of a quick recap here for those that don't really think about homological algebra very often. A DG vector space or a differential graded vector space is just a vector space, but its subspaces live in distinct degrees. And the idea is that we have some sort of linear map, in this case, Q sub G, that connects the subspaces in different degrees that are adjacent, and it squares to 0. In this case, it trivially squares to 0, because if you go from degree 0 to 1 with this map, and then you try to go from degree 1 to degree 2, say, well, there's nothing living in degree 2, so it trivially squares to 0. And of course, it's important to note that this differential encodes the equations of motion as a piece of data now associated to this sort of beefed up space of fields. So here's another level of abstraction. Again, please slow me down if people have questions, but this is really just terminology. So I'd like us to feel sort of comfortable with it moving forward without being too afraid. So if we take the collection of all of these graded space of fields such that they form fibers over the space of metrics, right? Then the idea is that we have a base space is the space of all, say, semi-Riemannian metrics on a manifold. And if we take the collection of all the fibers, where the fibers here are this DG spaces of fields with the differential, then this constitutes a differential graded vector bundle. In other words, it's just a vector bundle, but each fiber has a differential grading. For those of you that aren't super comfortable with vector bundles, again, I'm trying to make this as accessible as possible. You can think of a vector bundle as just a family of vector spaces, but it's parameterized by some background data. And in this case, or for a vector bundle, this background data has to be a manifold, right? But I think most of you probably have the basic idea. What can be kind of tough here is that this is a differential graded vector bundle. But this one is actually not so difficult to wrap our heads around because it's trivial in the underlying graded vector bundle part. The only thing that's interesting as we vary the fibers is that the differential changes depending on what metric G you're living above.
Question, Philip.
Yeah.
When you say it needs to be a manifold, do you mean a topological manifold? Do you mean a manifold with differentiable structure? Or
yeah,
whatever?
I mean a smooth manifold. Thanks. Yeah. In this case, anytime I say vector bundle or manifold in general, I'm always living in the smooth category. And it's of course worth mentioning here that the space of metric manifold, right? These spaces of fields, these DG vector spaces are infinite dimensional vector spaces. So I sort of swept it under the rug for this talk, but both the space of fields and the underlying base space, the space of metrics, are Fréchet vector spaces and Fréchet manifolds, respectively. So we can do the sort of basic notions of calculus in the infinite dimensional setting.
Okay, and this does not say anything about the space X, whether
no, I'm
that's
not.
smooth or not.
So that's a very good point. I am assuming that X here is smooth. I guess I kind of implicitly did that when I said that D is the space of all diffeomorphisms. So to have smooth maps, I think I was sort of taking it as implicit that X itself is smooth. However, I don't think I should have done that. Maybe I should have been more explicit. Moreover, I think it's possible, and I know this is of interest to you, Shadi, that some of these things would work out if we sort of loosened the assumptions on the smoothness of X. I think things would probably work out. There would just
I
be
think
more
it's possible to
Right.
take something which seems singular and put a differentiable structure on it such that it's smooth. I think that's possible. So
right, yeah.
whether you need this intrinsic smoothness may not be necessary. But sorry,
right, that's a very good point. I'm glad you brought it up. And I know it will be relevant going forward for me to think about stuff like that. So okay, great. Any other questions? This slide here kind of has a lot of information. But the point that I'm trying to make here is that, it's just a language. The parts themselves hopefully are concrete enough so that people understand. Okay.
So just one last question. Is it reasonable for me to think of this differential graded as having something of a model to think about, is to look at just like all the P forms on a manifold with the exterior derivative going from one to the other? That's an example of
it. Absolutely. The space of de Rham forms is a differential graded vector space. And if instead of, of course, we have the exterior derivative for de Rham forms, but if you take Hodge forms such that you have other differentials that depend on the metric, that would also constitute such a DG vector bundle.
True. Okay.
I have some more things to say, but maybe we should wait till after.
Okay, good.
I don't want to.
No. I thanks for that. Yeah. Okay.
But that was
I
a
have
really
some mental picture of what this thing could look.
That's a very good example, because I think a lot of us, when we learn about Hodge theory or about de Rham cohomology, we don't think of it as, oh, I'm doing homological algebra, right? A lot of it's just analysis and geometry and this kind of thing. But it is really sort of a canonical example of this kind of structure. In some sense, this is much easier, right? There's just things in 2 degrees and there's one differential. Okay. All right. So recall from an earlier slide that we had this equivariance property for the Laplacian. Well, the same equivariance property holds for the Laplacian with the volume form attached, this Q sub G. There's nothing really special going on there. It just follows from the fact that the Riemannian volume form has this equivariance property, even more trivially. And that means that if we have these fibers of these spaces of fields over distinct metrics, then we might have an isomorphism. In particular, if a metric G and its related fiber, this space of fields, is related to another metric via some diffeomorphism F, then that means we have this isomorphism. That's exactly this property here, that diffeomorphisms commute with the differential on the fibers. And using this vector bundle language, this is saying that, maybe I shouldn't go too much further down. It's just saying that we have a differential graded equivariant vector bundle now. So one of my sort of jokes is that what I like to do is I like to take basic things from geometry like vector bundles and add as many adjectives as possible. I promise I'm not just trying to confuse people. This is a legitimate way of thinking about things. So this here is often called diffeomorphism invariance in physics. And I think with the language that I know, I would prefer to call it diffeomorphism equivariance. However, I wouldn't say it's really an abusive language, because if you have isomorphisms, and what's important to note here is that we have the Euler-Lagrange equations, right? We have the critical locus of the Euler-Lagrange equations, and of course, the kernel of the Laplacian is the same thing as the kernel of the of this kind of souped-up Laplacian. The idea here is, although the space of solutions over the pulled back metric might look different, right? If you did measurements, you would literally see different data. But the idea is that it's the pullback of some data that's isomorphic to it. So that's kind of nice. And that all comes from this equivariance property of the Laplacian. There's of course a special case of diffeomorphisms which we need to be mindful of, and that's if we have isometries, right? So if you have a space-time X with a metric G, then we have a subgroup of the diffeomorphism group called the isometry group, and that's all of the diffeomorphisms that fix the metric G. By the above, the isometry group acts on well, it actually acts on the entire fiber. But in particular, if this thing on the left-hand side is 0, then it also preserves the critical locus sitting inside of the space of fields. In this case, it's sitting inside the degree 0 part of the space of fields. So let's just do a quick computation to try to keep things a little bit concrete. Of course, you can take Rn with its flat metric eta, or Minkowski space, right? Rn plus 1 with its flat Minkowski metric, but I'm doing the Riemannian case here. The isometry group for that is the semi-direct product of On, with Rn being the group of translations. So the idea here is that if we have such an isometry alpha, and we have a harmonic function phi, then its pullback along the isometry is also a harmonic function. This is, of course, a very significant aspect of harmonic functions when we learn about them. But here we see that it's in some sense kind of like a special case of the original one, where we have these isomorphisms between distinct fibers. Now, if you focus on just isometries, they're actually fixing the fiber, because as they're acting on the base space of metrics, they're not changing the one specific point, so that we just have an action on the fiber itself. Any questions on this? This is hopefully where things start to look a little bit more familiar, and we see how it's really a special case of the sort of language I've built so far. Okay. So I'm going to give a definition, and I know the word general covariance is very broad. So really, it's my definition that I think of in this context. But what we've shown so far is that if we have a family of that we might have a family of theories that's d-equivariant as a DG vector bundle over the space of all semi-Riemannian metrics. Just a quick note, because the differential operator that we've been using so far is a linear, like in the case of Laplacian, this is a free theory. So we're not really doing the interacting case. There is an interacting case, and the computations work just fine. And there is a definition, but I'll just show the one for the free case. And that's if we have a DG vector bundle that's defining a family of free theories, and if it's diffeomorphism equivariant as a DG vector bundle, then we call that theory a generally covariant theory. And it all really boils down to this diffeomorphism equivariance property of the differential on the DG space of fields, because the differential, of course, is the Euler-Lagrange form. So we're packaging a lot of stuff that's probably familiar, this kind of notion of having a symmetry of a field theory, but we're packaging in this like geometric language with a sort of flavor of homological or cohomological algebra. So just to summarize this far, we've talked about the traditional way, or at least traditionally for me, the way that I think of solutions to corresponding to each other is under equivalence by the isometry group of a Lorentzian manifold of a space-time, right? But now, given what we've seen, general covariance provides an expanded notion of equivalence. We're saying that if you add on some data, like if you will allow movement along the space of metrics, you might have some isomorphisms that you didn't see at first. So our hope is to package general covariance in a manner which also remembers the equivalences under the isometries of the metric. In particular, what I mean here is if we go back a slide, if we have a D-equivariant vector bundle over some space, then it stands to reason that we might guess that we could just look at a vector bundle over the moduli space of metrics up to diffeomorphism, right? But there's an issue, of course, is that we have stabilizers of the action of diffeomorphisms on metrics, such that if we just take the naive quotient, those isometry groups will be forgotten, right? Because the entire diffeomorphism class gets collapsed. But then when you try to rewind it, you might lose the fact that you had isometries in the first place. And as we know, isometries are an essential quality to know about to understand these theories. And so stacks here are very useful in understanding what's going on. So in the next few slides, I'm going to try to explain what stacks are, just for their own sake, but we'll eventually come back to seeing how they matter for us. Any questions here? Okay.
Oh, it's okay, just go on.
Sure. Okay. So first we need to say a few things about groupoids. You know, when I was first learning about these, I was definitely intimidated by anything that ended with oid. It was just too kind of scary for me.
Correct. We need to slow down.
Okay. But just in terms of lexicon, once you get over the scary names, they're actually somewhat concrete. So the definition is that a groupoid is a category where all the morphisms are invertible. So just as a quick reminder, a category is a collection of objects, and morphisms, right, are functors between those objects. Or sorry, not functors, just morphisms for now. A groupoid is the case in which anytime you have two objects and you have a morphism between them, you have an inverse to that morphism. So the way that I like to think of it concretely is that you have some collection of data, and the equivalences are packaged in the sense that all equivalences are present. If you have a morphism, you have an inverse morphism, right? You can't go somewhere without being able to come back in a well-defined way. So a classic example is the action groupoid. So if you have a manifold M and you have some Lie group, say G, acting on M, then we can define a category such that the objects are just the points on the manifold, and the morphisms are elements of G times M. In particular, what this means is that a morphism is, you know, if you fix an object, then the morphisms associated to that object is just the G orbit sitting inside of the manifold. So this is the action groupoid. And of course, because G is a group, all the morphisms are invertible because all group elements are invertible by definition. So I wish that when I learned about groupoids, this was the one that people first taught me about, but that's just not what happened. People tried telling me about the fundamental groupoid, which I understand, but this one I think is a much more pedagogically sound one to start with. And it really is the one that matters for us. Right, so just to reiterate, if you fix a point P, the morphisms are just a copy of the group. And of course, the automorphisms are the subgroup fixing P. So if you have a G action on M, you might have fixed points. To every point in a groupoid or every object in the groupoid, you have the automorphism group. And that's just, in this case, the fixed points. Or sorry, the subgroup that fixes P. The subgroup that fixes P. Okay, so the example, just to harken back to what we were saying in earlier slides, is you have the space of, let's say, Lorentzian metrics. You have the action of the diffeomorphism group on this infinite dimensional space of metrics. And so you can define the action groupoid. It's the category such that the objects are metrics, And at every fixed metric, the morphisms are just the diffeomorphism group. Either leaving the metric and having a well-defined way of coming back, or it just fixes the metric itself. Okay. So now a little bit more ramped up, but I promise it's not too important. I feel like I would be cheating everyone here if I didn't at least give a gesture at the definition, a proper definition of a stack. But actually, before I show that slide fully, how do people feel about what's on this slide here? Because if this somewhat makes sense, then we'll be able to just glaze over some of the more algebro-geometric mumbo jumbo, and this itself is the soul of the matter. Groupoids are the soul of the matter, I would say.
So far, so good.
Okay, great, okay. So there's an important maneuver thanks to Grothendieck and a lot of other of his, I don't know if you want to call them followers or cultists, in the 20th century, is that given some space X, a manifold X in this example, it's equivalent to its functor of points. The functor of points just means that instead of looking at a space X, you look at all possible maps from all manifolds into that space X. So this Ham here might just, in the correct category, this would be just differentiable maps, right? And the idea is that as you feed all possible manifolds into X, you recover the space itself. So the great sort of intuitive way of thinking about it is that, what kind of manifolds are there to send into X, right? Well, first you send a point, and then you send a line, and then you send a square, and then you send a cube, right? And if you send all of these manifolds into X, you see how we might be able to sort of reconstruct the manifold itself. This is done very, very precisely in the case of algebraic geometry. In particular, that's where these ideas were born, where instead of the category of manifolds on the left-hand side, we'd have the category of commutative rings, because there's the correspondence, of course, between a variety and a commutative ring. But it works just as well in the case of smooth manifolds, except there are instances in which a little bit more categorical machinery is involved. In some sense, it's just happenstance that the algebraic geometers found it first. Okay, but here's the key piece of data. When we take some manifold and send it into X, then what we get is a set. It might also be a smooth manifold, that's fine. But just to begin with, it's a set. The maneuver that's done with a stack is that instead of sending all these test spaces, the test manifolds, into set, so that Ham of whatever into X is a set, we define that it lands in the category of groupoids. In other words, we might be sending some manifold into another manifold, but we want to remember some equivalences, right? Remember, a groupoid is something with the equivalences built in. So this is the idea, is that you're sending a manifold into another manifold, but you have some equivalences you want to remember, right? So we might send a point. Let's say that you have, the circle acting on the two-sphere, and you send a point into the two-sphere, right? You could do that, and if you do the point, and then you do the line, and then you do the square, you recreate S2. But if you send the point into the two-sphere, but then it's actually the point up to a U1 action, and then the line up to a U1 action, and on it goes, that would be a groupoid. And so you'd try to remember the fact that U1, the circle, is acting on S2. It's also important that this stack, or even this functor of points, satisfies something called descent. This is just a sheaf-like condition, just gluing conditions on the original category of test spaces. Not really that important for us here. Okay. So this is a little much, but it's not too important to know this precisely. I just wanted to show people a basic outline of how these things get defined. The question for us, though, is really, what does a stack do? Once I've done this categorical mumbo jumbo and I've defined a stack, what does it give me? I would say it's quite nice. But here I'll motivate it with a fact that doesn't require stacks, is that if you have a manifold M, and if you have a Lie group G acting on it freely, so that there are no fixed points, then we have this equivalence. On the left-hand side, we have the category of G equivariant vector bundles on M. And on the right-hand side, we have vector bundles on the quotient M mod G. If the action of G on M is free, then we can take the quotient of, and that's again a smooth manifold, in which case we can define a smooth vector bundle over it. And you can prove with some kind of annoying long-winded computations that the category of vector bundles on M mod G, if you unwrap that, is the category of G equivariant vector bundles on M. Maybe some of you are beginning to see why this is important for us, because we originally would define general covariance as a property of equivariant vector bundles. Of course, we have an issue, right? And the action of the diffeomorphism group on the space of metrics has isometries, it has fixed points. So if we'd like to use a theorem like this above, we would need to generalize our notion of space. And that's exactly what stacks give us. So I'm not going to define a quotient stack, because that would take a long time and it wouldn't be useful. But I can tell you that it's an object so that for any smooth action, for any smooth G action on M, we get the sort of desired equivalence. So we have G equivariant vector bundles on M on the left-hand side, and on the right-hand side, we have vector bundles over the quotient stack M mod G. Of course, it takes time to define the notion of a vector bundle on a stack, but it's totally analogous to the notion of vector bundle on an ordinary manifold. There's just some extra bookkeeping, as I like to say to my students. Okay, so the soul of the matter is that we've moved into a new category, right? We have these stacks, but my philosophy, and I would say most people's philosophy, should be that we're just going to make use of these facts practically. By the way, just a quick note, there is currently an unexpected amount of landscaping happening outside of my apartment. So if it's loud or annoying, please let me know, and I will set up camp across the room. If it's not, then I'll just move on.
It's okay. I don't hear anything.
Fine, we don't hear it.
Okay, excellent. So I'll be annoyed to make up for the rest of us.
So,
Yeah.
Philip, can I just to trying to attach to some kind of a mental picture here?
Yes, please.
So if I have R3, let's say,
Yeah.
and I quotient by a translation, I get R2. So this, and you know, all the structures, I can recover all the structures on R2 in this way. Yeah. But this is because the action doesn't have any fixed point. Yeah. However, if I try to do it with a rotation, then I get the quotient object is not a manifold anymore. In some sense, it has a boundary. It has a that's right. It has a right.
That's exactly right. Yeah.
That's when we learn that there's something wrong with polar coordinates. That you get these singularities that are not really there, but they're annoying. They don't let you work around.
Right.
Them,
annoying for us in the sense that they're hiding information. By taking the quotient, you've lost something, right? You've lost the sort of fixed points. Right. And the stack remembers the fixed points. It's a new kind of space. It's scary to define, but whatever. It's a space such that it remembers what we'd like to remember. Yeah. So that's exactly the soul of the matter. That's a great example.
Okay.
Thank you for sharing. Yes. Yeah. Okay. I'm going to take some more water here. How am I doing on time? Okay, 12:45. That's not bad. I usually end up finishing a few minutes early, but it gives some time for questions, which I think are the most fun. So
don't worry about it. You have time. So
great. Yeah, fantastic.
No need to rush.
Okay, yeah, I certainly won't. So there's a really key example that I actually really like, and that's a point with a G action. Now, that seems kind of trivial, right? If you have just a plain point, you trivially have a G action on it. The point is fixed by the entire group G. However, if you do this with stacks, and then you remember that the point has this sort of G attached onto it, sort of in this sort of categorical invisible background, right? Then if you unravel the equivalence that we had earlier, then you get exactly this. that the category of vector bundles over the stack, point mod G, is the category of representations of G. This is kind of funny. It boils down to the fact that if you take an object on the left-hand side, via the definition, right, or sorry, via the statement of the theorem, you get that an object on the left-hand side is a bound. You have a vector bundle over a point, right? Well, that's a vector space. And on the other hand, it's equivariant, which means it has a G action. Well, what's a vector space with a G action? It's a representation of G, right? So this is really nice. When I understood this while learning about stacks, this is where I was like, okay, nice. It's a continuation of the joke that, you know, to learn linear algebra, you should just learn about vector bundles over a point. And this is saying to learn representation theory, you should just learn about vector bundles over point mod G. Of course, this is all wrong. If you try to teach your students this, they will end up being not mathematicians. But at the end of the line, certainly once we know these things, it's a good feeling. Okay.
The ones who will remain in your class,
Right.
will
Yeah.
cases, right? So.
Yeah, exactly. Yeah. Basically, what I'm saying here is, you know, don't let me teach linear algebra. No, I'm kidding. I actually love teaching that class. But right. So here's a bit of commentary, which, sorry, it's kind of a lot, but I think this is important, right? So obviously, such a fact is generally useful because the left-hand side of this equation is, well, I would call it geometry, right? It doesn't really look like geometry because vector bundles over a point are not that interesting, but it's still geometric via its initial formulation. And then the right-hand side is representation theory, which we all really know and love. And so I would say this gives us sort of common ground for ordinary symmetries, right? An ordinary symmetry meaning you have an isometry group of your spacetime and it acts on some equations of motion, preserves equations of motion, right? That means you have a representation. Your critical locus is, if it's a vector space, is a representation of the group. But now we're saying there's a more general sense. Maybe instead of point mod G, you had M mod G, where the initial point was a fixed point. So above that fixed point, you have a representation. But if you add some more data, like a metric or a connection one form, a background field, you get that these symmetries manifest in that sense. So I think this is something that physicists have seen a lot of, right, in our lives. That the example that comes to mind for me is that you might have some U1 action, but you don't get that it's a local action until you couple it to a connection one form. And then you see that you have this, you really do have a symmetry, even though initially it looked like it wouldn't work out. And this is where this is rooted. Okay. So now that we're experts on stacks, I'll give a definition of general covariance again. And as I like to say, this time with feeling. So recall that we have the diffeomorphism action on the space of metrics. We get an action groupoid. And remember, stacks are defined by sending test manifolds into groupoids. So we can define a quotient stack. This is the quotient space, M mod D, with the equivalences sort of remembered. So when we computed this equivariance property, recall that we also used an action on the fibers, which at fixed points gave us these representations of the isometry groups. And we concluded that we had a D equivariant DG vector bundle, right? So that was from earlier. Now that we have a quotient stack, we had this nice statement from a moment ago, we get that this descends to a DG vector bundle of the associated stacks, right? So earlier we said an equivariant vector bundle is the same thing as a vector bundle over the stack. And so now we have this equivalence and we could just say, okay, a family of free field theories is generally covariant if and only if it descends to a DG vector bundle of the associated stacks of the fields modulo the diffeomorphism group living over the metrics modulo the diffeomorphism group. And so that we don't forget the isometries, which of course are very important, we make it a vector bundle of stacks. And so this is precisely equivalent to the definition I gave earlier, but it sort of strips things away. It lets us say we have a vector bundle of quotient spaces without forgetting the things that we really like isometries. Any questions so far? I know there's quite a bit here, but hopefully.
So what I'm thinking of is that, okay, so going back to the free field example that you had, which was just harmonic functions, right? So yeah, we understand how the isometry preserves that. Is there, for example, is this going to help me discover, if I didn't know, the conformal isometries? Because that's a larger thing, right?
Yeah.
That maybe I didn't know about them, but will this help me, for example, discover those?
So I don't know if it would help. That's actually a really good question. Of course, part of what makes it an exciting question is that the word discover, right, is multifaceted. I don't quite know. I mean,
this information, what I just said, has to be in there somewhere.
Right. Yeah, exactly.
By your construction, totally, the conformal isometries also will be in there somewhere.
But is a conformal, I mean, I should probably learn more about conformal transformations, but is a conformal isometry?
So it means that the pullback of the metric, instead of being equal to the metric, is a function times the metric.
Right, that's right. Okay, so I think in this case, I would think it would be a very cool example to consider. I think in this case, it wouldn't be exactly the same, because then what you would like to define is metrics up to conformal isometries. And I don't know. Yeah, this is like a funny, almost like intermediate case between looking at diffeomorphism classes and isometry classes.
Right. So maybe this is for you to think about.
Yeah, no, but that's very good. I mean, it's funny you mention it, because recently, because I've been sort of bored with thinking about the same things over and over again, I've been thinking more about conformal maps. I will get back to you on that. I think there's certainly been some work done in this direction, within my sort of sphere of research. But I don't think
I was almost sure, because conformal field theory, it's a big deal, right? We just had a talk on Tuesday. We had a talk about conformal field theory here. Yeah. So that's why that's still on my mind. But go ahead. Sorry for distracting.
Yeah. No, it's good. I'm glad you brought it up. It'll give me something to think about and for us to discuss, of course, in the future. Okay. So yeah, just a quick sort of broad view of why this might be useful is that understanding the space of semi-Riemannian metrics up to diffeomorphism is a central problem in the literature, computing homotopy types and this kind of thing. It's commonly bumped into, and of course, the special cases is Teichmüller theory. Usually, I try to avoid saying the word Teichmüller, but I can't avoid it in this case. And yeah, so that's the special case when you think about Riemann surfaces. But of course, this has been considered in larger and larger contexts. And I guess one of the punchlines here is that techniques from physics, like looking at field theories coupled to metrics on that space-time, provide natural choices for what kind of bundles to consider over that space of metrics, or the space of metrics up to diffeomorphism, right? Like classes of field theories, for example, or families of field theories. So hopefully, as we might know from topology, looking at vector bundles over space gives us some sort of topological invariance. Hopefully consider these choices from motivated by physics also give some choices of invariance.
And let me just give a comment about the conformal invariance. Yeah. It's like this. When you consider these diffeomorphism, essentially you are looking for some kind of a topological information. Then you see you consider this diffeomorphism invariance, and then you see in conformal field theory the main thing that we want to consider only the conformal invariance. So it's actually smaller. You modulate some smaller thing, therefore the moduli space become larger. That is
yeah.
difference.
Yeah, that's right. Yeah. But it's right. So that's a very good point. But I still, I mean, in my mind anyway, I still view it as this like intermediary thing, right? Where an isometry is trivially a conformal isometry, right? But a conformal isometry isn't quite all the way general as a diffeomorphism, like you said. So it's this interesting intermediate that's worth considering.
No, I mean, I completely understand what Ija said. What the reason I brought that up is that my impression when you introduced the stacks and so on was that these things don't forget anything. They everything is remembered.
Yeah.
So so that's why I said, in some sense, the conformal things are also in there somewhere, right?
Yes.
So that,
yes, you're correct. Yeah, what you're saying is 100% correct. Sorry, it took me a few minutes, but now that we've been discussing it, yeah, they're in there. Yeah, I'll think more about this and get back to you.
I think they are in there. The only thing that what kind of invariance you are considering. If you want to consider the conformal invariance, then you get a conformal field theory. If you want to consider the topological invariance, then you get a topological field theory.
right.
So,
Yeah. Great, thank you. Yeah, that's right. Yeah, this will be great to think about moving forward. I'm glad we've discussed this. Okay, so far what I've talked about is this sort of global picture, the global picture of metrics modulo diffeomorphism thanks to stacks. But you know, if we have a manifold, like a manifold of all metrics, right, we might consider a tangent space at a specific metric. Similarly, if you have the stack of metrics up to diffeomorphism, you might consider, well, what's the analogous notion of a tangent space for such a stack? One would hope that it contains a little bit of quotient data, just like the global space itself does. And this becomes very, very useful when talking about current conservation. So just to continue our example from earlier, right? If we have a metric G, we can perturb it up to first order by a tangent vector at G. Some of you may know that the tangent space to the space of metrics at any metric is sections of sim squared of the cotangent bundle. Sorry about my weird notation here. This little caret means that we're taking the dual of the tangent space or the tangent bundle. We're taking symmetric squared sections. And so in the free scalar field, if you do this first order perturbation, then we get this quantity here. The 0th order perturbation, right? This is just basically the Taylor series, right? With respect to the metric up to first order. The 0th order term is just the action function from earlier, nothing special, evaluated at the base point G. And the first order term is, well, we're coupling this tangent vector to the energy momentum tensor, right? This is a first order back reaction to perturbing the metric. Sometimes called the stress energy tensor, whichever language you like, I'll stick to if people have preferences. And so the first term, as I said a moment ago, is again the action functional. And the second order term here, I'm going to call epsilon I sub G of H, right? Because G here, the metric, the base point metric, I'm still considering this like background variable. And H here is the key thing to consider. H is what we have control over in this context. So this is hopefully more familiar. And I'd like to tell you about why what I've been talking about so far is important in trying to understand this. But first, let's complete the calculation for those that need either a refresher or for those who this is new to. So if this perturbation H of the metric is induced by a diffeomorphism, then we get a special form of H. In other words, it's the Lie derivative of the metric G along the vector field V, where the vector field, of course, by exponentiation, generates some diffeomorphism. So the way that you should view it is that you have the space of metrics, you have a metric G, and you have a tangent vector at the metric G. Well, if you go along the diffeomorphism orbit, right, then you get that H is equal to the Lie derivative of G along V. So if you have a closed manifold X, I don't think I need to say exactly closed here. You could just consider functions that exponentially go to 0. There's a lot of ways of doing this. but just for the sake of the example, assume X is closed. Then the second term in that sum, the sort of stress energy term, is 0 whenever the matter field equations are satisfied. In our case, this would mean that the phis that we're sticking into are harmonic. Well, by some integration by parts, we get that this left-hand side here, H is LV of G mu nu coupled to T mu nu. Integration by parts gives us this. If this is to be 0 for on-shell functions, or for those that satisfy the matter field equations, we need this conservation law. If it's 0, then that must mean that the energy momentum tensor is covariantly conserved, that its covariant derivative is 0. This might be familiar to many of you. And of course, in this sense, we say that the energy momentum tensor is a conserved current associated to general covariance, because general covariance, again, is the symmetry coming from coordinate transformations. Whoops. Any questions here, or are we good? I'm guessing this is one of the more familiar territories for the audience. Okay. Now, we have a very important piece of data. If you have a quotient stack, you can associate to it something called the tangent complex. Now, the tangent complex is what's spit out by the quotient stack when you use the usual definition of a tangent space and apply it to a stack. By the usual definition, I mean, you can define a tangent vector to a point on a manifold to be the equivalence class of all curves, right? With a particular velocity vector, you could do the same thing. And then you get that the natural notion of a tangent object for a quotient stack is exactly, or sorry, yeah, for the quotient stack is this tangent complex. In degree 0, we have the ordinary tangent space of the manifold M at the point P. And the degree -1, again, very sorry about the notation. In degree -1, we have a copy of the Lie algebra of the Lie group G. And the differential here that connects the two of them, that makes it a bona fide cohomological object, is the differential, the exterior derivative of the orbit map, right? So at P, we send a copy of G into M, right? Via this action map or orbit map, or whatever you want to call it. And the differential in the tangent complex is exactly the derivative of that orbit map. Just a quick reminder, for some reason, it causes me a great deal of anxiety, this shifting notation. So the symbol brackets -k means you're shifting by k degrees. So this 1 really means that we're shifting by -1 degrees. Okay. It's hard for me to explain why, if you do the computation, this naturally falls into degrees -1 and 0. But for now, we're just going to have to take it for granted. Okay. Notice something interesting, by the way. This linear map between the Lie algebra and the tangent space can certainly have a kernel, and it does have a kernel if there are fixed points. So if there's some subgroup, big H, let's say, that stabilizes P in the action, then fractor H, right, the Lie subalgebra, would be the kernel of this map. It stabilizes the point infinitesimally. So the maxim that's often heard is that a tangent space is to a manifold as a tangent complex is to a stack. In fact, many people push it further and say, a stack is a space whose tangent object is a cochain complex. Excuse me, or a cochain complex concentrated in non-positive degrees. So this is honestly, I think, the most concrete way of trying to understand what a stack is, right? When you think of a manifold, you have a tangent space, you have a stack, you have a cochain complex. This is where I think understanding begins to happen. Okay, so there's an issue, of course, here. Let me bring it up before I go to the next slide. Because of homological computations, if you take two objects in degree -1 and you take their bracket, then they have to land in degree -2. But there's nothing in degree -2. That's kind of tragic, right? We have a Lie algebra structure, we have a Lie bracket on G, but if we shift it down to -1, then it has to be trivial. So what we do is we shift it back up. There's something called a formal moduli space or a formal stack, which is precisely this DG Lie algebra. We shift up the tangent complex by 1 degree so that the usual tangent space is in degree 1 and the Lie algebra G is in degree 0. Because homological algebra says if you have a bracket of 2 things in degree 0, it again lands in degree 0. There's no shifting going on. And so that's exactly the point of making sure that the Lie algebra is in degree 0. But otherwise, it's the same. I'm going to throw some symbols on the slides here, but don't be intimidated. I'll give an example on the next slide to make it concrete. We have these things called Chevalley-Eilenberg cochains. They're kind of weird to define, but the basic idea is that you just take symmetric powers, so really just polynomial functions on this vector space, on the dual of the vector space, shifted up by 1 degree. You could ignore this part of the slide because the basic idea is that this is Taylor's series around points in the stack, right? So if you manifold, you could take jets at a point, and we think of jets of smooth functions at a point to be the Taylor series, right? And there's an equivalence between those jets and symmetric powers of the dual of the tangent space. So we do a very similar thing here. We take symmetric powers of the dual of the tangent complex, and it happens to be these Chevalley-Eilenberg cochains. So this is a bit much here. And if someone has a question, please wait till the next slide, because I think the next slide will bring it back down to earth. There's a very important piece of data associated to this. So because this DG Lie algebra has a differential, if you take symmetric powers of this thing, it also inherits a differential. And if you work it out for a specific example, you begin to see why this is nice. So let's consider the case in which you have rotations acting on R2. It has a 1 fixed point, right? We get the infinitesimal rotation of R2, and this acts on functions by the usual curl vector field, right? You can compute some Chevalley-Eilenberg cochains. I don't know what they are. There's some complicated thing. But if you compute H0, right, this is the classic maneuver. If you have some big DG algebra or DG ring, and you're like, what do I do with this? You compute its first or 0th cohomology, and you see, is this something that I recognize? Well, if you compute H0 of the Chevalley-Eilenberg cochains for this action, you get the SO2 invariant, in other words, rotation invariant Taylor series at 0. So this is the key kind of thing to keep in mind. What I showed on this slide is a lot of scary algebra, right? But what do you do with scary algebra? You compute its 0th cohomology. And if you recognize it as something like, oh, this is just a rotation invariant Taylor series, then you know that whatever your big algebraic object is, it's just a derived generalization, right? A differential graded generalization of something that you're familiar with. Okay, so sorry for the quick rant that I didn't take questions, but I really wanted to just get this out on the screen. So does anyone have questions? This is a key object here.
So I have a more naive question going back to this degree business, which confuses me a lot.
Yeah.
If I have the space of P forms on a manifold, is that degree P to you or minus P, or what is it?
Oh, that's a good question. Naturally, I think it's in degree P. So if I were to be really, really pedantic, and I would write the forms degree by degree, I would say, okay, 0 forms in degree 0, 1 forms in degree 1, all the way up to top forms in degree dimension of X, right? But you're not wrong in sort of stating that this degree business causes some degree of anxiety, because when people make certain isomorphisms, they'll say, actually, reflect all the degrees so that that P would be a negative P and N would be a negative N and this kind of thing. But it really depends on what you're doing. And the only way that one really feels comfortable with it, in the words of Johnny von Neumann, is you just get used to it, right? So unfortunately,
I understand that if you have this structure that you keep taking taking the exterior derivative and you're going one way. Well, if you take the co-differential, then you're going the other way, right? If you take the divergence operator, you keep going the other way. So that's
right. Yeah.
So exactly. it is a matter of perspective. I just it's interesting that it's sort of sometimes these signs are the opposite of what we think they should be. But I guess that's what you have to get used to it, as you said.
Yeah, right. That's kind of the thing. And then often, you know, someone will take some sort of differential graded object and they'll shift it, right, or reflect it in some appropriate way to show that this that's familiar is isomorphic to something else, as long as you make some shifts or reflections. That's where it gets kind of iffy, because it sometimes starts to look contrived, right? Where you're like, why are you placing that in that degree? Why not this other degree? And I had these kind of pains early on when I was learning this stuff, and it eventually you just realized that you just place it in the degree that's most convenient. But it sort of seems at odds with the notion that there are instances in which there's a natural degree, right? Like with de Rham forms, this is a natural degree. With the tangent complex that I stated a few moments ago, there is a natural degree. The Lie algebra goes in -1 and the ordinary tangent space in degree 0. Yeah. So that's where a lot of the friction happens. All right, so the punchline is this here, that you might get some DG algebras, some DG objects. And again, the soul of the matter is that we're recovering a well-known object as the H0 of some derived object. And by the way, if you ever hear people talking about derived geometry, this is exactly what they're doing. You know, they're saying, you know, a derived manifold is just a manifold whose ring of functions is some differential graded object. Okay. And so the idea is that if you have a formal neighborhood, right, so one can interpret Taylor's series as functions on a formal neighborhood, on an infinitesimal neighborhood, but non-zero of a point, then we get that it's described by this differential graded Lie algebra, where in degree 1, we have the tangent space to the space of metrics. In degree 0, we have the Lie algebra of vector fields, and its differential is the derivative of the orbit map, which in this case is the Lie derivative map for the fixed metric G. Whoops. And then of course, if you compute H0 of the DG Lie algebra, not of its Chevalier, not of its CE cochains, this is the Lie subalgebra of killing fields, right? The infinitesimal isometries. I see that I'm running out of time here, so I'll move through a little bit more quickly. The rest of what I kind of wanted to say is that, you know, remember we had this DG space of fields from earlier, which was the fibers of this DG equivariant vector bundle. You can take the ring of polynomial functions, and this ends up being a Poisson algebra. There has to be some distributional completion, but we won't dwell on that too much. And of course, it makes sense that it's a Poisson algebra, right? Because this is supposed to package some classical physics. And with the integration pairing, this is actually a shifted symplectic vector space. And its ring of polynomial functions and the regime of my advisor and his advisor is interpreted as the DG ring of observables. So this is like a derived enhancement of the usual observables. And if you perturb the background metric, right, you have this the observables for this f sub g. You can perturb it for one order in epsilon h. And if the perturbation is induced by a vector field, then you actually have an equivalence of observables. And if you work out the precise maps necessary to state this isomorphism, all of the maps degree by degree, you know, in first degree, it's equivalent to the covariant conservation of the energy momentum tensor. And then in higher degrees, you have conservation of similar objects. And so this is one of the most concrete results, is that when you use this language of the DG Lie algebras, you get stuff that you would expect in this newer language. And of course, this is obvious when the Lie derivative of G is 0, because this term here is 0. The G plus epsilon LVG is just G. But this says that we have this equal footing between infinitesimal symmetries and perturbations along the orbit of a bigger symmetry group. And the DG language makes it precise. So just a quick recap, right? Remember, one can compute whether a family of free theories is d-equivariant or not. General covariance says, does it descend or not? If it descends, it's generally covariant. It descends to a vector bundle of stacks. And then if you do computations near a fixed G with this DG Lie algebra business with the tangent complex that I just described, it gives us current conservation results nicely. And if you interpret certain rings as derived observables, you get a good way to apply those current conservation results. The stuff about quantization is just looking forward. So maybe we don't need to discuss that as during the Q&A, but that's what I have for now.
All right, let's unmute ourselves and thank Filip for educating us on all this stuff. So that's